So let's see, now that we've made it through work and work kinetic energy theorem, we've now added another key problem-solving technique to our list. So let's recap where we're at. So far, we have 1D motion, and that would be with and without constant acceleration. So either we use our kinematics equations for the constant acceleration, or we use calculus for the non-constant acceleration. And then we have 2D motion, again, with constant acceleration or without constant acceleration. So with non-constant acceleration, basically. And so that was the beginning. And then we moved on and we saw that we had Newton's second law. And Newton's second law, we generally can just say we're going to use Newton's second law. We've seen how that applies to ramps. We've seen how that applies to circular motion. We've seen how that applies with friction. And so all of those sort of subsets of Newton's second law, they kind of fit nicely into Newton's second law. And then now we have another main one, which is going to be work. And a lot of times as the work relates to the kinetic energy theorem, so work kinetic energy. So one thing that I need to point out that is exceptionally important is that in terms of problem recognition and when you're going to use, for each part of a problem or each step, when you know to use work kinetic energy versus when you know to use 1D or 2D motion, work kinetic energy has no time in it. The force varies with position, right? So if it's a variable force, you would have F sub x as a function of x. So if you see information about force and position, then you're going to want to use work. So right away, when you see force and position or information about force and position in a conceptual question or in a problem, then you're going to start having that problem recognition that you need to start using work and work kinetic energy. So that's what we want to remember. Now, conversely, if you have force as a function of time, right, then remember that acceleration is equal to force divided by mass. And then you can use your 1D and 2D kinematics or calculus. Oops. Or calculus to solve that. But that's force as a function of time. It's very important to note that acceleration, for example, is dv dt. It's the time rate change of a velocity. So acceleration is not equal to dv dx, right? It's not the position rate change of velocity. That's not true. So you cannot use just an integral of velocity, of acceleration versus position, and then end up with velocity, right? So the integral of the acceleration dx is not velocity. So be aware and stay away from that pitfall. If you have information about force or acceleration with position, you need to analyze it from a work kinetic energy point of view. If it varies with time, then work kinetic energy is not the physics concept for you, and you want to use one of the ones that we've previously learned in this course so far. So add this to our repertoire of things that we'll use, and you'll have some examples of some combined concept problems which bring what we know about work kinetic energy along with what we have learned previously about 1D, 2D motion, and Newton's laws. Let me know if you have any questions.